You're having a good evening. Crouching music, hello, there we go. Okay, so I'm Michael Gutierrez, and if there's one thing that I've learned during my 4 years at Caltech, it's everything is wave.
Yeah.
Thank you.
We're doing a wave.
You guys not have that in it.
Well, why'd you stop? Keep going. Okay, so imagine you're me and you're in physics class. Now, the professor's writing equation after equation on the board at a breakneck pace, almost as if he was trying to fit the content of 15 weeks of a course into just 10. You tried taking notes for the first few lectures, but that went downhill real fast after the prof ran out of letters in both the Greek and Roman alphabets and started reusing them without warning. So V is for voltage, right? Why does that look like potential energy? It's the same thing. And what does any of this have to do with waves? That's what this class is supposed to be about. You try to raise your hand to ask for clarification, but nobody else seems confused, and the prof's like 4 blackboards ahead by now, so maybe it's best not to interrupt. He'd probably just say something like, "What, you didn't learn this freshman year?" Where is the beauty? Where is the elegance? Where is those seemingly those really interesting connections between seemingly disparate subjects? Those aha moments that make all of those hours of toil worth it. Those reasons that I switched my major to astrophysics in the first place. Well, they're scrambled up incomprehensibly on that blackboard somewhere, apparently. So you do what any good Caltech student would do in that situation, which is pull out your laptop and get completely distracted and start doing other work. So, if you're me and you're distracted in physics class, you're probably working on something for one of the 10 clubs that you're in. So maybe you have this little gadget that's like hanging off of your backpack. Oh, you know, I was gonna demonstrate it. Maybe you have this little gadget that's you pull out of your backpack and it's dangling off of your computer, and you're desperately trying to program it and make it cooperate. Dealing with Arduino code, it doesn't want to cooperate. Because this gadget tomorrow is going to go up on a balloon. We're going to put it on this balloon and send it up into the stratosphere, and we want to recover it eventually, so we need it to tell us where it is. It needs to take it to the GPS coordinates and tell us where it is. But there's 2 problems with that. First of all, in order to be allowed to transmit on the radio frequency of this global APRS, Amateur Packet Radio Service network, you have to have a call sign that's issued by the FCC. And in order to get that call sign, you have to pass the test. So you're probably here during class, just like doing the study guide for the amateur radio exam, and asking yourself why you thought iambic pentameter was an instrument that could be used to determine the standing wave ratio. But presumably, once you get past that, it'll be a cool full circle moment, because actually my grandpa was a ham radio operator, and when I was a kid, he used to have this whole radio set up in my grandparents' garage, and I used to look at those and marvel at it and wonder what kind of wizardry was going on inside. So that'll be cool to actually have my own call sign. But after that, there's still another problem, which is that this gadget does not come with an antenna. So here's the analogy, right? So say this thing here is the gadget, and it has all of these signals, that the information, the GPS signals that we want to send it down to the ground. But right now it doesn't have an antenna, so basically when it sends the signal, the signal just bounces back it bounces right back into the circuitry, and that's a waste. We don't want, there's not that much power, so we want to conserve the energy. So we need to make an antenna. So if we put on just any old piece of metal, just like a bad antenna, then maybe some of the wave will go out, but a lot of it will still end up bouncing back and forth inside. So we need to build a good antenna, which will act like an open window. So all of our signal will go from the wires and into the air. So we could go to Amazon and buy an antenna and give money to Jeffrey Bezos and kill some trees. That would be easier. Or we could do the fun thing, and the fun thing that's actually related to waves, and we could build one ourselves. Yay! We're finally back to waves, the wave equation, I love it. So yeah, like I said, we need to take these voltage and current signals, and then we need to turn them into electromagnetic waves. And you can't just do that with any old piece of metal. You need, well, the simplest way to do it is a dipole antenna. And so you need two pieces of metal that are 1/4 of the length of the wave. In this case, the wave is 400 megahertz, so the wavelength is 70 centimeters, so we need two pieces of metal that are 17 centimeters in length. I don't want to go to a hardware store and buy that. So what if we just use a tape measure that we have lying around? That'll probably work. So we get two pieces of, cut up a tape measure and electrical tape it onto a wire, and there's the antenna for our gadget. So, long story short, so we send it up into the air, and I pull out my ground station antenna and the ground station gadget, which I haven't even told you about, this whole other thing. And we wait to see if we get signals from the balloon. And we do. It actually makes it up to 24,000 meters altitude, which is pretty good. And presumably it made it higher, but that's when the battery died, or at least for some reason we just stopped hearing from it. And yeah, we never saw it again. It's more in the desert still. Yeah, so lesson of the story here is that it's actually pretty difficult to make a gadget that will reliably transmit information even in harsh conditions. It's much more fun, I think, to build the ground station side of it, which does the receiving, and because that's where you can get tricky with all kinds of different strategies to increase your signal to noise ratio. Anyway, so if you're me, then you've probably already lined up a summer internship at MIT Kasich Observatory for the next summer, and they already have a satellite in orbit that they've built, and it works and it transmits. It does really cool science. It studies the northern lights, but that's a different thing, because what you're really here for is the big satellite dish, 38-meter satellite dish that you get to play with the receive electronics for. Whoa. And so you end up designing this whole ground station interface software, which takes the signals and then it turns the analog into digital, and it turns it into ones and zeros, and then theoretically into packets that tell you how the spacecraft is doing. Except the radios that are on the satellites are actually proprietary radios made by this company who really wanted us to buy the $30,000 pre-built ground station instead of making one ourselves. So it was hard to figure out the specific decryption packet system, which wasn't the same thing that was in their data sheet for it, and it's just a mess. The digital side, the digital stuff is not for me. I much prefer to do the ground station side of things. So you're back in physics class after summer. You feel like you thought you had mastered the science of waves and all of that, but supposedly this class is supposed to be about electromagnetic something or other, but there's still no sign of the wave equation. So distracted again, and maybe you're looking out the window at this satellite dish, which is just on the roof of the building next door. And actually you wonder if you could play with it, because nobody actually has used it since the radio astronomy department moved out of the Moore building 10 years ago and moved to Hazel. It's just been out there. So you ask the electrical engineering department if you can play with it, and they're like, sure. So this is really cool. Now we can do radio astronomy. So, and it's much easier than transmitting information because all you have to do is receive it. So you just have this nice big dish that collects all of the electric field and focuses it onto this one antenna. And the electric field makes the current go back and forth from the antenna, and it puts the current through a resistor, and the resistor heats up because it's a resistor. And so you just measure the temperature of the resistor everywhere you point in the sky, and you can make a map of the sky. Whoa, that's cool. So that's all well and good, but there's another type of signal that you can look at in radio astronomy, things that change, things that go bump in the night, things that flash, they're there and gone. They're called fast radio bursts, and they last like a millisecond, and they don't repeat. You have no idea where they're going to pop up in the sky, and they're really hard to detect. We don't know what causes them. So, you know, the dishes are pretty good for picking up a lot of the signal from one specific point in the sky, but really we want to be able to see as much of the sky as you can at once. So if you're me, then maybe you'll spend a year, like a summer, and then the rest of an academic year designing an antenna, a special antenna to do just that. So we've got this weird dual polarization dipole thing, which has this massive field of view. So other antennas like the parabolic dishes, maybe you can see as much as like this little red dot or the blue dot at any one time. But this antenna can see this whole red circle at any given time. That's like half of the visible sky. Huh. So we're gonna be able to see all kinds of signals popping up. It's gonna be excellent. Except there's not just one of them. There's let's see here. There's going to be a lot of them. There's going to be 256 of them. Man for scale. Oh god, this Blender model is like probably going to crash my computer. So, but you get the idea. Yeah. So then, once you do all you plug that antenna into the digital stuff, which fortunately is not my job, then you see a fast radio burst, and it looks like that, and it sounds like a sad trombone. because that's what happens when waves travel through the dust and gas of space. They get spread out like that. And then when you have 256 antennas and they're observing for a long time, then you can see a lot of fast radio bursts, and eventually you can start to map out the universe based on the shapes and like the amounts of dust they pass through. And so eventually we get to a map of the universe just from waves.
Cool.
So I'm not exaggerating when I say the whole universe is waves.
Yay!